All right, here is our example problem. I have a tank. And this is going to be port 1, and this is going to be port 2. Okay, and I'm going to tell you what's happening here at state 1. I think a good way to do things is just label the states and put it all into a list. I like to put my states into a list because it helps me figure out really what I have here. And I know that the velocity of 1 is equal to 20 meters per second. The area of 1 is equal to 10 times 10 to the minus third meters squared. The pressure at 1 is equal to 20 bar. And the temperature at 1 is equal to 600 degrees Celsius. Okay? And as the screen updates, I'll go ahead and talk about state 2. The volume of 2 is equal to 1 meters per second. The area of 2 is equal to 6 times 10 to the minus third meters squared. The pressure at 2 is equal to 10 bar. And the temperature at 2 is equal to 150 degrees Celsius. My question is this at steady state? Now, you might look at this problem and say, Dr. Wanklin, it's not at steady state because the velocity in is equal to the velocity out. Is not equal to the velocity out. But that is not telling us what steady state is. Steady state is that to figure out the mass flow rate in is equal to the mass flow rate out. Okay? And so, I need to figure out what mass flow rate is 1 and mass flow rate 2. Okay, so here we go. Mass flow rate 1 is going to be equal to volumetric flow rate 1 divided by specific volume of 1. Okay, now, I have been given area and velocity. I have not been given my specific volume. How do I find my specific volume? Well, I have to set my state. Okay, so when I go here, I'm going to go to 220 bar and 600 degrees Celsius. And let's go ahead and do that here. Let me see if my document camera is available today. Hopefully, come on now, big money. No, it's not. Darn it. I don't know why it's going on with that document camera. So let's just look at it. Just take a pause for yourself and go look. If we go to table, well, I can draw this out here. This is my 20 bar. Okay, you should be able to go to 20 bar, and you can see that 20 bar we saturate at 212 degrees Celsius. And so we're well above that. We're up here at 600 degrees Celsius, so that means that we are a vapor. So I'm going to go to my 20 bar entry, and I go to 600 degrees Celsius, and I can find my specific volume here, that my specific volume at 1 is going to be equal to 0.1996 meters cubed per kilogram. That's what I'm going to have there. Okay, so I looked up, used the properties that I could do to find out what this is, and I can find that m dot is now equal to 20 meters per second times my velocity, or times my area, which is 10 times 10 to the minus third meters squared, divided by my specific volume, 0.1996 meters cubed per kilogram. Let's look here, meters cubed, you're going to cancel. I'm going to have kilograms per second, which is what I want. And I can find this is going to be equal to about 1 kilogram per second. There's my screen update. Sorry about this updating thing. I've been working on trying to figure out how to make this not occur, and I haven't been able to figure it out yet. I'm using some Ethernet cables, and it's not really working out so well for me. Okay, so that's 1. So we have to see if mass flow rate 2 is going to be higher, lower, or the same. Okay, so my mass flow rate 2 is going to be the area 2 times the velocity 2 times the specific volume at 2. Okay, so the big thing here is going to be setting that state. So I'm going to start that for you, and then I'm going to let you go and work on the rest of it yourself. Now we're going to look at this and we're going to say that here's my vapor dome. We're going to be at 10 bar. And we look at 10 bar and we go back to our tables. 10 bar is going to saturate at 179. Okay, we're below that. So we're a liquid. All right, we're a liquid, but we are well below what the liquid tables give us for water. Well below where we're given at water for table A5. So what do we do? What do we do when we don't have a liquid table for the property that we've been given? The answer is, like you said, liquid approximation. I heard you shout it out. Approximation. And what we're going to say is that the specific volume at 2 is going to be approximately equal to the specific volume of the saturated liquid at the temperature I've been given. That is what I'm going to use. At the temperature I've been given, not the pressure. And I'm going to put it into here. Okay, so I want you to look that up. I want you to do this calculation. And I want you to determine, is this at steady state? Okay, is mass flow rate in equal to mass flow rate out? If it is, you say yes, it's steady state. If it's not, you say no, it's not at steady state. And that will be your answer to today's quiz for this problem.